Yeah, thanks for having me. It would have been really nice to be in India again. I had a great time last year, and there was a really good hospitality as well at the conference in the spring at the ICTS as well. And hopefully, yeah, in the future, after all this is over, we can reconvene at some point in India. But yeah, anyway, so I'm giving the part two, building on the previous discussion that Derek was talking about. First, I'm going to give some brief motivation for the chiral phase transition and why it's kind of interesting to study. So just in other words, the chiral phase transition, what you're doing is you're characterizing it by the formation of this chiral condensate. So this Q bar Q. And it has this particular symmetry breaking pattern. So your left and right guys are breaking down to vector SU2. And in the chiral limit, so when you take quark masses to be 0, this symmetry breaking pattern is exact. And in particular, what you see is you have massless Goldstone modes, which are the 3 pions. But in the real world and in QCD, we know that the quark mass is not 0, and this chiral symmetry is not exact. And in fact, the pion mass is around 140 MeV. But nonetheless, we can ask, can we see any signatures of this? And there's kind of 2 avenues of saying this. So the lattice points to yes, there's some evidence that points to a transition, that this transition is in the O4 universality class. And potentially in future experiments, if we're near the critical temperature, maybe some of these soft pions can escape and in this way provide a measurement window to these chiral dynamics near the phase transition, so these chiral critical dynamics. So this plot, Derek has already talked about actually, but I can just say a few words on it as well. So this is kind of like a thought experiment. I mean, a lattice computation where they took the physical parameters that we have in the real world. So the ratio of the strange to the lightest quarks is here, and the pion mass is 140. And they did this computation in an O4 model, and you see that you kind of have this behavior. And then kind of you can say, well, what if the chiral symmetry was actually realized in the real world? What would the susceptibility is plotted against a function of temperature look like? And what you would see is that, okay, they drive the pion mass down until it's almost 0. I mean, they get down to 55. And you kind of see that this, this peak starts moving lower down. So the critical temperature, where you have the transition moves lower down. And also the susceptibility becomes steeper. So you're really almost becoming delta-like when you really take the pion mass to 0. So there is some signature of this from this hot QCD collaboration. And yeah, also Derek shared this plot. So like he was saying before, so if you just look at the soft pions, you have these fits, and these hydrodynamic models have problems trying to resolve the low PT pions. And their traditional approach of just adding more resonances marginally improves the situation, but they still quite can't close the gap. And yeah, with the maybe taking into account these chiral critical effects, maybe we can close this window down so that we're actually back at 1 again. And on that front, actually experimentally, so as Derek said before, Elise is kind of the only place which is really doing this low PT kind of measurements. And what's happening, well, next year, hopefully, is this, there's this upgrade that's happening during the long shutdown to the ITS detector at Elise. And this is this inner tracking system. And this allows a higher sensitivity to low PT particles, so especially soft pions. And yeah, that's just a plot from the technical report. They are currently on ITS 2, and with this upgrade, they'll go down to one of these red lines or the green lines. I think these are, red line is kind of the minimum, and the red line is kind of better. But anyway, the standard observable that you would be measuring is to kind of have an insight into this chiral physics. This chiral critical physics is this multiplicity ratio of charged to neutral pions. Or for instance, you can look at the correlation function between charged pions. And like I said, the upgrade was scheduled to be by the end of 2021, but I mean, given the world's uncertainty, we don't know exactly when that might be. Maybe this is delayed by a few months into 2022. Okay. Kind of like a snapshot of what we're studying here. It's this hydrodynamics and the chiral limit. So what we're looking at is at long distances. What you're kind of ignoring the finer detail of QCD. You just say you just ignore all of the phenomena which are shorter wavelength, and you just model all of your QCD effects by some hydrodynamic theory. But what we do now is we include on top of that some modes, which are like that are of length the inverse pion mass, and you kind of have this picture of these hydro modes representing QCD physics with this extra superfluid modes on top that are at the order of, well, the momentum is at the order of the pion mass. And the question is, how do these extra modes contribute to and change the underlying QCD hydrodynamics, in particular the hydrodynamic variables and the transport coefficients? And what we'll see by the end of this talk is kind of a teaser, is that the hydrodynamic variables get this correction due to the pion mass. So for instance, we'll compute the shear viscosity, and the QCD theory, so this hydro theory that's kind of underlying, the underlying description has some transport coefficient, which is you can determine in advance, and we'll now get some correction coming from these superfluid modes. So yeah, then I can tell you about the ingredients in our model. So this is following work by Son and Stefanov. And here I'm just referencing Son, but also Stefanov has done some work on this. And the kind of the major ingredients are you have the conserved quantities, the energy momentum tensor, and the axial current. You have this chiral condensate, which you can write in polar representation. So sigma is this amplitude, and u is the phase. Or you can also, as I'll be writing during this talk, it's you can write it in this Cartesian form. So phi alpha, tau alpha, where tau is a vector of Pauli matrices. So like tau 0 is the identity matrix, and then you have tau 1, tau 2, tau 3, which corresponds to the different Pauli matrices. Then you also have these the standard hydro variables. So you have a temperature, you have velocity, and you have chemical potentials, mu left and mu right. And you also have this explicit breaking mass for the Goldstone boson, which we need to make kind of contact with the real world, because the chiral symmetry is only approximate in the real world. Okay. So also Derek mentioned that this work goes back to Rajagopal and Wilczek. So this is the O4 free energy, which will be the basis of what I'm going to be talking about today. So when you're, so you have some free energy, and when you're near the critical temperature, so when you're near a phase transition, you can kind of decompose it into the free energy into two pieces, a regular piece and a singular part. The regular part near the phase transition is finite and doesn't really care much about the critical behavior, whereas the singular part does, and it in fact is the piece that's capturing the critical behavior. So we're going to focus on trying to study and understand this in more detail. So this is what we would write down as our singular piece. Oh yeah, so the regular part is coming kind of from QCD, and this is kind of the superfluid part. And so you can see here that we have these superfluid degrees of freedom. So mu alpha beta is the O4 chemical potential, and in particular, so the alpha beta are the O4 indices, which might be a little strange, but I just wrote them out explicitly. But for instance, like if you look at mu 0I, you see that this is just the axial chemical potential squared. So this is exactly what Derek had in the previous talk, but written with the O4 indices explicit. Then you have this gradient term of the O4 vector, which is just the sigma and pion field. And so, and this is just related to the sigma by, just to remind you, again, by being dotted with the Pauli vector. And finally, you have a potential term. And this is where we modeled the phase transition behavior. So you have a mass term, you have a quartic interaction, and you have also an explicit breaking term. And this mass term will depend on the reduced temperature. So when you'll be able to kind of interpolate between the two phases of between a broken and an unbroken phase based on the value of the temperature. So what we'll be doing is working in the mean field approximation to get some nice plots going. And the way you do this is really straightforward. I'll just outline the basic steps. What you do is you minimize the potential. So you take the derivative with respect to the O4 vector. And I'm dropping indices. This is a little sloppy, but you basically arrive at something like this. So this is the amplitude, sigma bar. And you can solve this. And what you find is that this sigma is given by, in terms of this reduced magnetic field, which is just the kind of explicit breaking term that we've included, times the scaling function f g of z. And z is this variable, which goes like the reduced temperature times the reduced magnetic field times to the power of these critical exponents, beta and delta. And since we're going to be working in the mean field, it makes sense to use the mean field exponents. So that's exactly what we do. We take beta's 1/2 and delta's 3. And then the this dynamic, this variable z now has this power h to the minus 2/3. Right. So this scaling function that I introduced before, so how the mean value of the amplitude changes is plotted here. There's been so it's plotted against this dynamic variable z. And just to remind you, this is what fg of z is. It's just sigma bar h to the minus 1/3. And the way to understand this x-axis is just to remind you, it's taking you between the broken and unbroken phase. So on the left side, you have t is less than tc, and on the upper side, you have t is larger than tc, and 0 is when the temperature is exactly at the critical temperature. And yeah, so there's this you've probably seen there's these two lines. This red line here is what we compute. This is the mean field value, just coming from minimizing the potential. And then these gentlemen here did a similar computation on the lattice, and they get this dotted line. So that's kind of maybe a more precise input. But you see that the mean field kind of captures the right behavior. So in the vicinity of the critical temperature, we actually agree exactly with the lattice. And if you go further out for larger and smaller than the critical temperature, there's at least qualitatively the right behavior. Right. And so now what we're going to do is continue in the mean field approximation. And we're going to expand our chiral condensate around the mean field value. So you have sigma bar is the mean field value, and you'll have a variation with, you'll have a delta sigma here, and you'll also have this phi. So delta sigma is kind of the variation of the amplitude, and phi is the phase to linear order. And again, tau A are the Pauli matrices. And now what we do is we take the free energy that I alluded to before, and we can expand to quadratic order. So what you see is you have so the full free energy, you'll have the regular piece, and then you'll have chemical potential part, and you'll have the quadratic terms in delta sigma, and you'll also have the quadratic terms in the phase. It's important to point out as well that the regular piece gets a contribution from the mean field. So kind of the naive thing that we wrote down. So the QCD hydrodynamics, which are kind of captured in this F regular, now get this added contribution that are coming in from our expansion around the mean field. So kind of the singular piece is now really just the singular piece, which is given here. And everything else that's finite has been kind of packaged away into this F sigma. Right. Okay, and now I can tell you about the different parameters that appear in this action. So what we've kind of done is, here are some of the physical quantities of interest. So here we kind of introduce this mass here, which is the Pions screening mass, and it's just given in terms of the magnetic field and the mean value, the mean field value sigma bar. And if we can also write this in a different way. So we can write this in terms of the explicit scaling function the plot of which I showed you previously, this fg of z. And mc squared is a constant. It's the value of the mass on the critical line. So when z equals 0. So this is just another way of writing the Pion screening mass. But we also see that sigma has a screening mass as well. And the form is a little different. So you'll have this m sigma squared is, again, given by this critical value on the of the mass on the critical line when z equals 0, and then with these this explicit function of c. And finally, you have multiplying everything. You have this of the Pion sector. You have the Pion velocity squared, which Derek was discussing previously, and it has a particular simple form. It's just given by sigma bar squared over chi naught. So to kind of take a closer look at the Pion screening mass and the sigma screening mass, I've provided this plot here. So again, this is comparing to the gentleman from the lattice again. And what you have, the red lines are, again, the mean field values, and the dashed lines are the lattice. And again, we're plotting against z. So large negative z is the broken phase, and large positive z is the unbroken phase. And you see that for in the broken phase, the lattice and the Pion mass squared really agree quite well. And as you go into the unbroken phase, there's actually some deviation, but qualitatively the picture is captured pretty well. And likewise for the screening mass at the asymptotia, so you can't really see this, these guys agree very well, but the qualitative picture is exactly what you would expect. So the minima are aligned, and you have m sigmas growing as well as it is in the lattice. So those are kind of the ingredients that we'll be using to compute eventually the hydro coefficients, the transport coefficients. Okay, and now from this free energy, we can compute the equations of motion. We'll have 3 sets of equations. First, we'll have the partial current conservation, which Derek mentioned before. So the axial current, will be given by, will be conserved up to this explicit breaking term. We'll also have this dissipative Josephson constraint, so we'll have the phase being given in terms of the chemical potential, and we'll also have this dissipative chemical potential. I'll get to that in a sec. And we'll also, we have this diffusion equation for the condensate. Or rather I should say the amplitude. So dt sigma will be just given by the variation of the free energy, the singular part of the free energy with respect to the sigma. And we also will add some noise. So I kind of got ahead of myself on this slide. But the linearized equations of motion, they look like this. So you'll have a set of coupled equations, which are the ideal partial current to axial conservation, which I just gave on the previous slide, and also the Josephson constraint. And what we do is we add dissipation following a careful analysis of the entropy production, which also, this is kind of a snapshot of what Derek was talking about before. So the ideal part is given here. So you just have the Ji will be given by a gradient in the gradient in the phase. But if we add dissipation, we'll have some gradient also in the chemical potential. And we add some noise to balance this dissipation following the fluctuation dissipation theorem. And also this Josephson constraint, which is written now in the linearized regime. You'll have the time derivative of the phase given by the chemical potential. And then we also have some dissipation and noise. And yeah, here's the linearized axial current as well. So that's the whole set of equations. It's just putting these two pieces together. And furthermore, we'll also have this diffusion equation for the condensate, which is not coupled to the phase nor to the chemical potential directly. So it just has its own equation at the linearized order. Right, okay, so what we can do is we can take just to take a closer look how you solve the system of equations. Of course, you can just write everything down in a matrix form. So here's the phase phi times some factor omega k, and you have chemical potential mu alpha, and it's sourced by some noise. And you have these contributions which are dissipative. So this is gamma k squared plus m squared and d naught k squared. And what we do is, so this is where the fluctuation dissipation theorem comes in. So you have your variances. So the noises have vanishing mean but non-zero variance. And the variance is just given by the dissipative contributions here. So gamma k squared plus m squared and d naught k squared. Just writing this in a bit more compact way, I just call the dissipation with respect to phi, I call it G1, and the dissipation with respect to the axial chemical potential, I call it G2. And what you then can do is you can compute the whole symmetrized correlator for the mu and phi, and it looks like this. So this is analytically done with these shorthands, but I mean, that's not very important for the purposes of this talk. Instead, kind of just to give a snapshot of what we compute, we find, okay, then we have a phi correlator, a phi mu correlator, a mu phi, and a mu mu. So phase, and chemical potential. And we'll also have a separate propagator, which is for the amplitude. So for the sigma, with also this sigma screening mass appearing here. Okay, and now what we can do is we can take a closer look at one of these propagators, and yeah, good. I didn't know if I added the slide. So if we plot one of the propagators, so this G mu mu sim, with these where we use the shorthand, just to kind of get a feel of what's happening here. The plot kind of looks like this. So you'll have I don't know if you can see, I can't really see the top. Okay, yeah. So this is the spectral density for the axial charge, density correlator. But basically it's the expression I showed previously. It's just the correlator. Okay, now this plot is a little different. So this is plotted against the frequency divided by some constant. So that's what the overbar denotes. And the different curves correspond to different temperatures, basically, or for different z. So if you first look at z equals 16, this is when you're in the unbroken phase. And you just have this one sharp peak in the middle here, right? And kind of what you see is as you drive down z, as you go towards negative values of z, the peak becomes less and less pronounced, and eventually you start seeing the formation of these two peaks. And eventually, for large negative z, you have these two peaks. And kind of the interpretation of this is, for large z, you have this diffusion of quarks, but now you kind of have a different propagation when you're at low z. You can kind of interpret them as being a pair of propagating pions. So you kind of see in this plot, it's kind of really nice, is this transition from kind of QGP physics, so for large temperature, to pion propagation, to like the broken phase. So that's just kind of neat. And now what we're going to do is we're going to take these correlators that I was just talking about. We're going to compute these hydro loops. And this is done in a very standard way via the Kubo formula. So the shear viscosity is given just in terms of the shear components of the stress tensor, but without loss of generality. We're going to take them to be in the XY direction. The isovector conductivity is also just the anti-commutator of the isovector in the X direction. And the bulk viscosity, which I'll talk a bit more in detail, is given by this kind of product of these O bulks, this particular operator, which I'll talk about later. Okay, and so the computation kind of proceeds in the same way for all of these cases. What I'm going to do is in this talk, I'm just going to focus on giving a brief snapshot of how you would do this in the case of the shear viscosity. And the other ones are exactly analogous. The isovector is a little simpler and the bulk viscosity is a little bit more complex. But kind of the logic is the same. So in the case of the shear viscosity, you're going to be looking at diagrams like this. So you'll have some insertions from the stress tensor and you'll have propagators. So you'll have another diagram as well. You'll have G phi phi and you'll also have G sigma, G sigma. And you see that by looking at the stress tensor. So this is something that Derek also had on his slides before. You'll see that you'll have this ideal piece where the energy density and the pressure have been redefined. So they contain the free part, and they'll also contain contributions from the superfluid energy density. And you'll also have this microscopic degrees of freedom explicitly written out. So in terms of the chiral condensate. And when you linearize this and you look at the XY direction for the stress tensor, you'll get two contributions. So one is coming from the amplitude, so from delta sigma, and the other one is coming from the phase. So this is kind of the condensate contribution, this is kind of the pion contribution. And there's no mixing between these two. So that kind of simplifies computations. So you kind of can break up the computation into pieces. Remember, this is to quadratic order. So this is the correction of the shear viscosity. And you'll get two, I call them I's, two integrals. And so kind of the first integration goes like this. You'll have your propagator, which is given in this way. So you have your omega squared plus this dissipative term. And so the kind of like a diffusion pole. And this is the formal expression that you need to integrate. It's just the usual picture. You integrate out everything except for the K integral, and kind of the subtle point is you see that it's divergent actually. So you need to introduce a cutoff, and this is no big deal. What we can do is we can expand for a large cutoff, and you see that there's going to be a piece which is like linear, so it's divergent. in momentum, and there will be a finite piece, and there will also be subleading terms. But in the limit where lambda goes to infinity, where the cutoff goes to infinity, of course, you don't really care. You just can discard these higher order terms. Okay, and likewise, you proceed with the phase. So you have the phase correlator, the phi correlator, which is given here with these various coefficients, with these dissipative terms. So G1, G2, and there's this gamma Q as well, which is just the sum of the dissipative terms. And this is kind of the simple structure which appears. And again, you need to integrate just like what you would do with the stress tensor. So in the XY direction, you just integrate XY and with this propagator squared. Yeah, and the result is like before. So what you'll have is a divergent contribution going like lambda, and you'll have a finite piece and also other subleading terms, which we'll just ignore here. And yeah, just for compactness, I introduced some other variables. So R squared is given by gamma divided by gamma plus D naught, and you have U squared, which is basically the pion velocity. And there's this function f, which is just this integral here. So this is a finite integral, which evaluates to this combination of u and r, and it's a symmetric combination of u and r because you can see that in the denominator. You have this k squared plus r squared m squared, k squared plus u squared m squared. So you just get the symmetric combination from these two guys. And this is the reason why I didn't want to get into like the bulk viscosity, for instance. The expression becomes very large and a bit unwieldy. But what you can do is you can now add up these contributions from the amplitude and from the phase, and you find a very simple expression for the shear viscosity. So you'll have this eta physical sigma, and you'll have which is the piece that's coming from your underlying theory, and as well as it captures the cutoff dependent piece. So kind of the divergences get put into your shear viscosity, and you'll have some extra corrections on top of that, and that's given by, you see you have a pion mass, you'll have the pion screening mass, the sigma screening mass, and this function which is proportional to the pion mass as well. And okay, just to see what this looks like, we can put in some numbers. So this is similar to a plot that Derek showed previously. So this dashed line is kind of the result from our previous work. So this is for in the broken phase, you do this computation without including the amplitude, and you kind of see that the effect of the change in the shear viscosity. And you can also take a look at doing this computation in the unbroken phase, and you see this is what this orange dotted line is. So you're taking at very large values and of temperature. Okay, and so what you see is the behavior, just as Derek mentioned just before, that the shear viscosity is in fact growing, and it's growing quite slowly, and then it starts falling off when you go to large temperatures, so for large Z. So that's very neat. And you can repeat this procedure as well for connectivity. You can take a look at, again, the Kubo formula is given like this. And the J here, the current is, the isovector current is just written like this. So you have you only have the pion contributing here. So you just have a phi gradient phi term. And all you need to compute is something like this. So you'll have the conductivity is given by this leading piece, so the regular piece plus this correction. And plotting this correction, you see that this actually is a plot that Derek showed just in the last talk. Again, you're kind of going in the broken phase. You have some value of the conductivity, and as you transit the critical temperature, it starts approaching zero rather rapidly. Right. And finally, you can take a look at the bulk viscosity. It's just a little bit more complicated. But the relevant, but also very straightforward to do. The relevant operator is O bulk, which is CS squared. So which is CS squared, and the 0,0 component of the stress tensor, and the spatial trace divided by 1/3. And the reason why you choose this is rather than say the trace, which is what you would expect to use for the bulk viscosity, is that you can take the limit rather smoothly when the momentum goes to 0 with this operator, but you kind of have trouble doing that with if you just took the trace operator. So this is kind of a more well-behaved operator in this sense. And yeah, then you can take a look at the stress tensor to compute this O bulk. And what you'll see is that O bulk is just given like this. You'll have some contributions like the pressure, the chemical potential will be entering, the pressure again, and you'll have also the microscopic fields making an appearance. So the whole thing becomes a bit more complex. There's a few more integrals that you need to do. And what you end up seeing is a very, well, kind of nice plot as well. So what you see is that the bulk viscosity is kind of peaking right around the right around z equals, well, right around the critical temperature. So the contribution really is kind of maximal around here. And yeah, like I was saying before, this dashed line represents the kind of computation that we were doing previously. So you see that this is quite steep, quite steeply falling, which is exactly as predicted. And also we have this asymptotic computation when you're in the unbroken phase. Right, and kind of summarizing the change in scaling, what you can do is you can take this the individual transport coefficients, the corrections to the regular part, and divide it by the kind of unbroken phase value of the correction, which we can also compute. So everything is normalized to 1 in the unbroken phase. And we kind of now play the game where we're bringing down the temperature, and now you're going past z equals 0, and you're looking at what happens at the small tc value. And what you see is you kind of have this ordering of the isovector conductivity has, I don't know, around 15% change from its asymptotic value, and then the shear viscosity has a much more significant one, but the most significant is on the bulk viscosity, which kind of is indicative that the bulk viscosity is quite important near the chiral phase transition. And you can see this further by taking a look at this plot here. So this is a plot of the ratio of the bulk viscosity over the shear viscosity. And what you see is that the difference between them, especially in the region of the phase transition, is quite significant. And kind of this is illustrative. So I mean, this parameter that we're dividing by, or we're multiplying by the difference, is something like 46. So this is kind of the susceptibility in some sense. And yeah, so this kind of tells you that you expect the bulk viscosity to really have something to say near the chiral phase transition, and is worth considering. So I think that's all I wanted to say today. If you guys have any questions, I'm happy to answer, or Derek and I guess, are happy to answer if he's still around.
Thanks, Alex. It was a very nice pedagogical talk. So we are now ready to take questions. The first question will be from Chiral. Maybe he can ask himself.
Hi. So thank you very much for the very nice talk. I think I'm just missing a bit, and I think I confused something. But anyways, I will still ask that. So maybe building on Zoran's previous question about the pi-pi interactions, or the interactions between the pions. So when you're below the TC, the critical temperature, then of course you can neglect those interactions, and mean field theory is fine. Now I don't remember anymore how you treat those pi-pi interactions in this work. Since you are crossing zero and z becomes positive, I don't quite remember. Do you take them in full, or what exactly is the truncation again in the Lagrangian Pions?
We don't have pi-pi interactions in that sense. So we just have yeah.
So is then the approach still applicable? I mean, I would understand if you are below TC and you neglect those interactions. However, especially around TC, and it might be problematic, right?
Right, but if you're just looking at like kind of the thought is that you just have the softest pions that are present, right? Around TC, so the interaction shouldn't be that important, right? That the interactions themselves should be quite weak there, or quite insignificant in some sense. Yeah. So I mean, it's something that we definitely need to include if we're going to actually put this, say, in a hydrocode or something like that. This will be something that's worthwhile to include, of course. But you can see here, so what I've put up is you just have this kind of the pion sector, right? So you just have, you don't have any interaction terms. You just have kind of the pions times some pion velocity. So
right, which is kind of mean field.
It's mean field.
It's mean field, yeah.
It's mean field. I mean, below TC, it goes beyond mean field. Well, mean field's applicable, right? You just have pions, and they're kind of Gaussian theory. And the treatment here of the critical region is, of course, mean field. Everything mean field. And how good is that? Well, oftentimes qualitatively, it follows kind of not too bad, right? So as far as understanding the basic trends of how the parameters go, I think it's pretty good, right?
Right. That's why you were comparing to the lattice. Okay.
Right. And I think that's what but of course, to really get the right critical exponents and the dynamical critical exponents, then you need to simulate.
Thank you.
Okay, Sayantan will be asking the next question.
Hi, Alex. Thanks for the nice talk. So I was wondering, you had this stochastic noise term also in your hydrodynamics. What is the significance of it, and did you use it anywhere in the later analysis, or?
Yeah, I mean, this is just to compute the correlators. This is just formal, basically, to arrive at this, I forgot I can't point, to arrive at this symmetric correlator, pion, and well, to arrive at these correlators here, you just kind of set up your equations, and what you'll end up doing is you need to invert, like on a technical level, you need to invert this matrix, and then if you compute the 2-point functions, you'll see that you'll have sigma 1, sigma chi1, chi2 correlators, chi1, chi1 correlators, and chi2, chi2 correlators, and you need to say how these guys are, what their correlations are, so what their variance is, and basically that's where their use is. That's how you build up this symmetric correlator. That answers your question.
Thanks.
Okay.
Okay, so are there any further questions?
Yes,
if I could maybe say about that last question.
Sure.
Okay.
Just, I mean, of course, the loop involves this the fact that you have a hydrodynamic loop, right, is the noise, right? Because somehow the fluctuations, which are then interacting non-linearly a little bit.
Right.
Yeah. Okay.
Okay, I have a very, if I may, I have a very dumb question, or I guess I just got somehow lost. So what does the dynamics of your pions and your sigmas actually look like? Do you have a plot of their spectral function? I mean, mainly what I'm wondering is whether it's sort of a diffusive dynamics, or whether you have them as quasi-particles essentially somewhere.
Right. So let me see if
I think for the sigma, I see it here basically, right?
Yeah.
For the sigma, it was basically there, right?
Yeah.
Right.
Yeah. So that's diffusive. For the pions, it looks like this, right? So you have this two limits, right? So
this is actually the pion. Okay, good.
Right. Or yeah, and kind of you see that for large temperature. So for large Z, it looks diffusive, but then as you go down in temperature, you actually have these two separated poles.
But I guess if you were to include loop effects, right? I mean, you would have some kind of thermally generated mass also, right? I mean, it's basically that your mean field mass drops to 0 as you lose the condensate, right? That's why your peak goes in, right? So I'm not sure that this would actually kind of persist at higher orders. Isn't that what's happening, or? So,
so can I?
Yeah, go ahead.
All right, so first of all, this is the axial current correlator.
And, so that's not the pion, yeah.
And so at low TC for Z very small, right? Sorry, Z negative, right? It is the pion. They're related to each other by some trivial factor.
Okay.
And above TC, you only have diffusion, and it is strictly in the massless limit, strictly conserved. And that's why you see that you can't generate a mass, because it's axial current conservation, right? And it has to go like dk squared.
Yeah. Okay. Okay. No, I mean, I was wondering for the.
And if you do the same plot for the pion, then you see that it becomes equal with the sigma.
Exactly.
Right?
Yeah.
And you will see that, right? That at high Z, at large negative Z, it's going to have these peaks, and then at large positive Z, it's equal to this spectral density of the sigma, which you saw there.
Okay, I see.
But if you look, and that's kind of what's neat, is that somehow, it's mixing. If you look at the axial current, right, initially it's complete, those two modes, the axial current correlator and the pion field, are completely uncorrelated, right? The spectral density is, you have this matrix that he was drawing there is diagonal. You have one for the pion that's equal to the sigma, and one for the, wherever it was, this matrix. Yeah, if I go to the matrix, just well below TC. If you go to the next slide, maybe.
Yeah. So
well below TC, it just becomes diagonal. And the two terms on the diagonal are unrelated to each other. One, the phi correlator becomes equal to the sigma 1. And the mu correlator just becomes the simple diffusion. And now as you go below TC, then, the phi correlator and the mu correlator become sort of maximally mixed.
Yeah, okay, gotcha. Okay. All right, perfect, thanks. I think that gives me a clearer picture of the dynamics.
Hey, Sayantan has a comment which probably Derek has already addressed. Maybe Sayantan, you can ask it.
No, it's fine. It was just a comment. So.
Okay.
Yeah, I mean, I think the lattice, if I can comment about that, the pion screening mass is really very precisely measured on the lattices. Thank you, as you guys know. And that puts some reality constraints on what you could possibly, how small the sigma mass could be, right? But it's okay. It doesn't bother me too much. Somehow, it's roughly consistent. But it definitely puts some serious constraint. I mean, the lattice and specific measurements of the pion mass and the dispersion curve really, really constrain this whole possible variations quite strongly. I mean,
So related to that, right? I mean, so so assume you were to somehow miraculously get input for, say, the pi and sigma spectral functions also, right? You could actually calculate their contributions to the transport coefficients also, right? With non-perturbative input, right?
Yeah. I mean, somehow already the screening masses that they measured.
No, I mean, just, I mean, assume you really have, I mean, I don't know, you have more non-trivial structures in the spectral function or something like this. Right?
Yeah, why not? Why not, right? So instead of doing this one loop calculation that we did with kind of these propagators, you could put in more non-trivial spectral functions, right? And
yeah, that's interesting.
And if you had it also, especially if you would want to, I mean, this coupling between the pion and the axial charge, right? That you would want to have in, right? Just have the right physics.
Yeah.
Right. But at least that part we can get with the mean field, which is nice, right?
Okay. Thanks then to all the speakers.